Hello, my name is Yuri Lavinas. I'll be talking about this work entitled Resource Allocation and Population Size in MOEA. The summary of this work is that we compare the population dynamics of MOEA with resource allocation with the general MOEA with different population sizes. And our conclusion is that MOEA with resource allocation converges to the Pareto Front at about the same speed as MOEA for a small population, and explores the search space more like an MOEA with a larger population. So before I get into more details, let us review what multi-objective problems are. They are problems with more than two objective functions. These objectives often conflict with each other. This means that if we improve one objective, we decrease the other. To solve these kind of problems, we can use evolutionary algorithms. And one very common and popular algorithm is the MOEA. The main important characteristic of MOEA is to decompose a multi-objective problem into multi-subproblems and solve them all together. Okay, so here is an example of the decomposition of MOEA. We have a multi-objective problem with two objectives, F2 and F2 and F1. And we create 5 subproblems, S1, S2, S3, S4, and S5. In this case, S1 is 0 times F1 plus 1 times F2. S2 is 0.25 times F1 plus 0.75 times F2. All other subproblems are created in a similar manner. The idea is that by creating those subproblems, we can distribute our solutions well in the objectives place. The original MOEA distributes computational effort equally to all subproblems. And we can make MOEA to focus more on subproblems using resource allocation methods. So an example is that given 500 evaluations, the general algorithm gives 100 evaluations to each subproblem. If we sum the resources of all subproblems, we still have 500 evaluations in total. With resource allocation, however, we can have a different distribution of resources. So for example, we can give 200 evaluations to S1, 50 evaluations to S2, 7 to S3, 80 to S4, and 100 to S5. If we sum them up, we still have 500 solutions, but as we can see, this distribution is completely different. All right, one way of dealing with resource allocation is to use priority values, priority functions. Priority functions establish preferences between subproblems for resource allocation. They help us to guide which subproblems to focus more on. And they allow us to design different variants of MOEA that focus on the desired characteristic. Now I'm showing you an example of resource allocation in our multi-objective problem that I showed before when explaining the decomposition. Here again, I use the same subproblems as before. In this first generation, we sample random values to each of these solutions. And solutions with a higher priority function value are shown in red. They are the ones that are going to be selected and candidate for change. So as I said, we select only those 3 solutions. The other 2 are left unchanged. And then we update these 3 solutions. So we enter generation 1 and move to generation 2. In the generation 2, we sample new values, new priority function values for all of these solutions. Again, solutions with a higher value are going to be selected and are shown in red. As you can see, the solutions changed. The solutions with a high priority function value changed. So we select only solutions with a higher priority function value, leaving the other 2 unchanged. And we update only the solutions in red. So this is the example I showed about resource allocation. Okay, so in this work, we're addressing also population size. So let's review a little bit about it. The population size has a deep impact on the dynamics of and performance of any evolutionary algorithm. As we know, the right part of the population size depends on many characteristics, such as difficulty, presence of local optima, and shape of the Pareto Front. A too small population size can cause premature convergence. However, a population size that is too big may cause the algorithm to waste computational resources. In specific, in MOEAD, this choice of population size also defines the number of subproblems, and each one of these subproblems might have different characteristics in a multi-objective problem. How does resource allocation and population size relate to each other? So, resource allocation can ease the burden of choosing the right population size, because when we use MOEAD with resource allocation techniques, we can have a bigger population size, but we update only few solutions at iteration, as I showed before. In this work, we use the n-partial update strategy. We call it PS. We use it to verify how much of the performance improvement in MOEAD with resource allocation is given to the fact that is updating only a small number of solutions for a much larger population. The PS strategy allows MOEAD to select any solutions to update at its iteration. This is the algorithm of MOEAD PS. It is the MOEAD with the n-partial update strategy. It has a new input, the n parameter, which is a user-defined parameter. All the other inputs are the traditional inputs of the MOEAD. After initializing the variables of MOEAD, we keep running the main loop until the termination criteria is met. In line 4, we generate random values, as I showed before in our example. In line 5, we select n subproblems with the highest UI value. In line 6, we do for each subproblem selected, we generate new candidate solutions and evaluate these new solutions. After we do that for all subproblems selected, we update the set of solutions. We highlight that even if a solution was not selected to change, it might be updated because of the characteristics of MOEAD. Okay, we did a complex experiment to verify if the population size, if the dynamics of updating a small fraction of the population size is one of the reasons why MOEAD PS performs better. So we use MOEAD PS with a population size of 500 solutions, and the n input parameter is set to 50, 10% of the population size. We compare it with MOEAD with a big population. In this case, the population size is 500, the same as MOEAD PS. And we compare also MOEAD with a small population size. In this case, the population size is 50, the same size as the number of solutions updated by MOEAD PS. The experiment was conducted in the inverse DTLZ 1 to 4 functions, each with 100 dimensions. And we evaluate the performance using the hypervolume metric. In our experiment, we give 30,000 evaluations to each algorithm for solving each multi-objective problem. Here I'm showing the Pareto Front approximations of the invert DTLZ1 on the left and the invert DTLZ3 on the right. MOEAD with a small population is shown in blue circles. MOEAD with a big population is shown in gray triangles. MOEAD PS is shown in green squares. As you can see on the left side, MOEAD PS has a very good approximation compared to the other two algorithms. While on the right side, it's very competitive with MOEAD with a small population. I want to talk about the differences in empirical attainment function. But before that, I want to explain what they are and how does it work. The empirical attainment function allows the examination of solutions of many different sets of different runs of an algorithm. this function illustrates where and by how much the outcomes of two algorithms differ in the objective space. So here I'm showing where the objective space is dominated by solutions of MOED with a small population. And here I'm showing where the objective space is dominated by solutions of MOED PS. Okay, so this is the differences in empirical attainment function between MOED with a small population and MOED PS in the invert DTLZ1. We can see that MOED with a small population performs better than MOED PS because this region is dominated by MOED PS in at least 20% of the runs, because the shade of red that we see here suits the interval of 20%. On the right side, we can see that MOED PS outperforms MOED with a small population in this region of the decision of the objective space, much closer to objective 2, at least 80% of the times of the runs. We can see that the performance of these two algorithms is complementary, as MOED with a small population is better for objective 1, and MOED PS is better for objective 2. However, for the same function, the performance of MOED with a big population differs a lot to the MOED PS. As you can see, MOED PS dominates all regions in at least 80% of the runs, while MOED PS with a big population cannot perform better than MOED at any region of the decision space. Any better performance in the objective space. Here I'm showing the hypervolume anytime performance of the algorithms in the DTLZ, invert DTLZ1 and invert DTLZ3. On the right is the invert DTLZ1. On the left, on the left is the invert DTLZ1, and on the right is the invert DTLZ3. Again, MOED with a small population is shown in blue circles. MOED with a bigger population is shown in gray triangles, and MOED PS is shown in green squares. On the left side, on the invert DTLZ1, we can see that MOED PS is the anytime performance of MOED PS is closer to MOED with a small population, and after around half of the executions, it outperforms, becoming the best algorithm in this problem in terms of performance of a hypervolume. On the right panel, we can see that they are very competitive, MOED with a small population and MOED PS. In any case, MOED with a bigger population doesn't work too well. In terms of final results and hypervolume values for the invert DTLZ1, 2, 3, and 4, we can see that MOED PS is the best in 3 out of the 4 functions. In the DTLZ3, it's not the best, but its performance, it's very close to the performance of MOED with a small population. We can see that it has a more stable results. It performs well in all of 4 functions, while the others, MOED, perform well depending on the problem. In terms of non-dominated solutions, we can see that the MOED PS finds a higher value in any case, with almost 100% of the solutions being non-dominated. So in conclusion, we show that MOED PS progresses with the search as an algorithm with a small population size and explores the search space as an algorithm with a big population size. MOED PS provides an effective approach to mitigate common problems related to the choice of population size, as we can set a very big population size and update small values during the search. So this is the end of my presentation. Thank you for your attention. For more information about me, you can scan the QR code on the left side and access my website. On the right side, you can scan the QR code to the QR code to access the GitHub repository with the code of these experiments. That's all. Thank you very much.